All right, so now I'm just going to revert back to our table. We're going to deal with the coefficient in front of the x, b. Y is equal to f, open brackets, bx. It tends to be a little bit trickier. So this is a horizontal stretch about the y-axis by a factor of 1 over b. So just to recall, here, our blue was our parent graph, and what we're able to see is that A was 2. Sorry, my mistake. B was 2. So this implied that we stretched by a factor of 1 over 2, or compressed by a factor of 2. Yeah, so this could get interesting very quickly. Let's go back to this. And first things first. So given a graph of y is equal to f of x, we're going to denote the domain and range. We're going to sketch the graph of the following transform functions. And if we could do that, this is fairly straightforward. We're going to write the mapping notation x, y. We're going to describe it in words, the transformation. And note the domain of range of the transformed functions. Now, b is equal to 2. And I always find it's nice if we can figure out what's going on with the point notation. So here I'm going to say, well, b is 2. This gets goofy. We would normally like to think that this is, well, we do know that it's a horizontal stretch, but it's a horizontal stretch by a factor of 1/2. So that's kind of important. So point xy would get mapped into point x over 2 comma y. So now the y values don't change. It's the x's that change. How? We take the x value and we divide it by 2, or multiply them by 1/2. Your choice. So let's jump on the graph. So right now, if I take this point and I take a look and try to understand this point notation, -2, 3 changes into -1, 3. Why? Because the x value was multiplied by 1/2 or divided by 2. 0, 0. The x value is divided by 2. 2, 1. Well, to compress this or stretch this by a factor of 2, we divide the x value by 2. So it becomes 1, 1. And now 4, 1 is mapped into 2, 1. And my graph looks something like this. Goes from, and it has to stop right here. So I'm just going to highlight, my graph goes from here, 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 and then here. And there's my transformed graph. We can say that it's been horizontally stretched by a factor of 1/2. Equally correct, you can say it's been horizontally compressed by a factor of 2. That's the same thing. The domain. Well, the domain of the pink graph, it was -2, 4, but magically it goes down to -1 to 2. Well, that makes sense because we compressed this by a factor of 2, stretched by a factor of 1/2. My range, guess what? My range remains the same because the transformation was on the x, not on the y. Last but not least, and hopefully I'm not taking up too much of your time, k of x is equal to f 1/2 x. So this, I think, is going to be better to write out in words first. I'm going to stretch, better put a word in front of there, horizontally stretch by a factor of 1 over 1/2, but this is probably better known as 2. 1 over 1/2 is horizontally stretched by a factor of 2. And just for clarification and just to make this so much easier to look at and to write, I'm just going to erase this and just do the graph all over again. So I have point x comma y, and how does this point change? Well, we change it into point 2x comma y. And this might make sense. We horizontally stretch by a factor of 2. All right, so I'm going to take this point right here, and this point is -2, 3. I'm going to multiply the x value by 2. It turns into -4, 3. My origin 0, 0 remains at 0, 0. 2, 1 is mapped into 4, 1. Now, my old point that was at 4, 1 would be mapped into 8, 1. So, I made my graph way too small. But anyways, this is now my new graph that is stretched by a factor of 2. Isn't that interesting? How does my domain change? Well, my domain is changed because I'm stretching horizontally by a factor of 2. And if I take a look at my original domain, way up here, and I'm going to compare it to my transform domain, it's -4, 8, inclusive of the endpoints. My range, sorry, this is the domain and range for a previous function. My range actually remains the same, 0 to 3. And there we have it. There are your transformations. So if we revisit this transformation just very quickly, reflections and stretches, if you take a look at the mathematical operations, you're always multiplying either the x values or the y values by some constant, but you're multiplying. So I call these the multiplicative transformations. And if we go back to way up here, transformations of functions, horizontal translations, these were the additive transformations where you just added a constant to either the x